Well, AP students, buckle up, grab your equation sheet and calculator. It's time to get on the kinematics grind. It's Mr. Simpkins back in the Simpkins Physics Corner. I got to go warp speed because I got 15 minutes, and I want to show you as much as I can. So here's our equations. This is the fourth and secret kinematic equation that's not on your equation sheet, but sometimes comes in handy. And here's what all of those variables mean. Let's jump into it. A car is speeding up and has an instantaneous velocity of... All right, so we're at the beginning of the problem. That's going to be v initial x, 1 meter per second. All right, and it's speeding up, and it says in the positive x direction. So we're looking at our coordinate system being right positive. When a stopwatch reads 10 seconds, it has a constant acceleration of 2 meters per second squared in the x direction. Question A says, what is the speed when the stopwatch reads 12 seconds? And question B says, how far does the car move between 10 and 12 seconds. All right, so we have some, gotta love that. We have some initial time, which is 10 seconds, and we have some final time, which is 12 seconds. Now, you could go ahead and use those t final, t initial, but as you know in all of our kinematic equations, they just show t, and what they really mean is the change in time, the delta t, which would be 12 minus 10, or we're looking at a time interval that lasts for 2 seconds. So that's the important part there. All right, so let's go ahead and jump into it here. That says it has a constant acceleration of 2 meters per second squared. So we'll write that in our list of knowns over here. And the first question says, what is the speed when the stopwatch reads 12 seconds? Now remember the enlightenment moment. Sometimes what you don't know tells you more than what you do know. All right, so we're looking to solve for this Vx at some point, right? And we don't know anything about the distance. So as I choose my equation for the first one, I'm going to go ahead and try to avoid anything that has x in it, which would be this one and this one. You see it has x initial, so does this one. I'm going to avoid those because I don't know them. Sometimes what you don't know tells you more than what you do know. And what I do know is that I don't know x, so I'm going to pick this equation right here, plus ax times t. All right, so let's take a look at this. Remember, the Vx is the final speed. That's what it's saying. What is the speed 2 seconds later? So that's the one we're solving for. I'll just leave it there. V initial x is 1 meter per second, and then we do plus the rate of acceleration, which was 2 meters per second squared, and we got to multiply that by how long we were doing that acceleration, which was for 2 seconds. And if we put that all together, Vx equals 1 meter per second, plus we changed our speed by an amount of 4 meters per second, and of course our V final, or our final speed, would be 5 meters per second. Not too bad for the first one. Next one, how far does the car move? Okay, how far is talking about distance or displacement, and that tells us about x. Now remember, sometimes what you don't know tells you more than what you do know. But other times, what you want to do is you want to look at the equation that most simply finds the thing that you're looking for. And so what I mean by that is check out this equation, all right? It already is solved for x. Could you use the bottom equation to solve this problem? Sure, but then you'd have to be square rooting and multiplying and subtracting. No gracias. So I'm going to switch colors for this second part here, and let's go ahead and find out the distance that we traveled in that interval. Remember, we made a rule when we first started talking about problem solving that if it doesn't tell you the exact starting position of an object, you have permission to go ahead and make the starting position 0, because it's just a convenient place to start a problem, of course. And so if I fill in this equation right here, I take the final position is going to be 0 meters, that's x initial, plus, all right, here we go, v initial x, so that's 1 meters per second right there, and then we have times time, which was 2 seconds, so we'll drop that guy in there, and then we have to add it to this last term here, sorry about that, this last term plus 1/2 a is going to be our 2 meters per second squared, and we got to multiply that by t squared, and t was 2 seconds, so don't forget to square that last term. And notice, only the t is squared, not the entire thing. Some people get overzealous with that. So we have x equals, and we're looking at, there's a 2, and meters per second times seconds would be meters, so the units work out there, and then plus 2 squared here is 4, times 2 is 8, but half of that is back to 4 again, and so our final answer for this one would be 6 meters. So here's a fast, quick, easy example of how to use the kinematic equations to solve for, hey, how fast are we going after a certain amount of time, and how far do we go after a certain amount of time? Yo, we are flying. We're only at 4 minutes, 30 seconds. Let's keep grinding. 2 farmers driving their cabbage carts. I mean, who doesn't do that every weekend? They're moving from the same starting point in the positive x direction with constant accelerations. The silver, so let's see. So they're both starting here at the same place. Positive is to the right. They're both starting at the same place like this. The silver cabbage cart has an initial velocity of 2 and an acceleration of positive 4. The black cabbage cart has an initial velocity of 6 and an acceleration of negative 0.4. Find the time at which the silver cart just overtakes the black cart. Now, this one is all about strategy. This one all is about setting it up in a way that is going to allow us to keep track of everything well. And so I'm going to color code this. I'm going to say, well, silver, I guess I should use, here, actually, do I have gray? Is that an option? Because if it is, that would be dope. Of course it's not. Well, we're going to make gray purple. Yeah, why not? So we're going to turn this into a purple cabbage cart. There it is. It has an initial velocity v0x of 2 kilometers per second and an acceleration of 4 kilometers per second squared. And then we got the black cabbage cart. I do have that font color. That's going to be an initial velocity of 6. And it's going to have an acceleration of negative 0.4. Okay, so what we want to do to be tricky about this is the question is saying find the time at which, so we got to solve for time, all right? And so I'm going to go ahead and say we're not going to be able to use that equation, at least not right away. We can't use that right away. But we want to solve for the time that both of these things are in the same place. So here's what I'm going to do. We know they start in the same place, so we're going to call x initial for both of them 0 meters, all right? And I can do that for purple too, but unnecessary because they're the same. But I'm going to call x final the thing that they share, okay? So watch what we do here. I'm going to write an equation using this one because we want to know the time at which they cross one another. I want to write an equation for each of these. So let's see how this works. All right, so the same x is going to be true for both of them because that's where they meet each other, equals x0. They both start at 0, so that makes it nice. And now here we go. All right, we have v initial x, and we're talking about the black cart for this equation. So that's 6 kilometers per second. And then times time, which we don't know, plus 1/2. And the a is negative 0.4. All right, I'm going to do some bad physics etiquette and maybe not write the units for every step, but I'll do my best not to do that too much. Okay, so that is the equation for the black cart. Now let's go ahead and write an equation for the gray, aka purple cart. That one would be x equals 0 plus, all right, this has different numbers now. It's going to be 2 here and a t. And again, I'm going to drop the units just for the sake of time, but don't do that. That's terrible strategy. And then I'm going to write acceleration of, oh, sorry, it's 0.4, and it's positive point, all right, sorry, so this guy has a positive 0.4, this guy has a negative 0.4, so that one's good. This just needs to change like that. Okay, good. Now we're on track. Now hopefully you're not getting too confused. All right, now what are we looking at here? Well, what we can do, ladies and gentlemen, is because this x is the same as this x, and how do I know that? That's because we set up the problem that way. We said they're going to cross paths when it overtakes the black cart. That's when they're at the same position. So they have the same final position. And what that allows me to do is to say 2t equals, or sorry, 2t plus, there should be a plus sign there, 2t plus, all right, 1/2 of 0.4 is going to be 0.2, of course, right? T squared equals, I can set these two, I can set these two expressions equal to each other. And that's a really nifty strategy because watch what happens. Then we have this other guy is going to bring to the table, it's going to say 6t plus, and I'm coming from here, so that's going to be half of negative 0.4 is going to be negative 0.2 t squared, okay? So what I just did is I set the black equation equal to the purple equation. Why? Because they were both equal to x, and we defined the final position of both cars as with the same x. Okay, now here's what's a pretty cool thing that we can do. You may factor out a t from either expression and then divide both sides by t. All right, well, what does that look like when you're done? Well, this term has a single t and this term has a t squared. This has a single t and this has a t squared. So imagine dividing every term by t. As long as we do the same math to every term on every side, that's a legit math move. Watch what happens. 6 minus 0.2t. All right, keep track of all that. And over here, we have, oops, oh my goodness. Every time I tap my screen, it wants to jump 5 slides ahead here. And then over here, we have 2 plus 0.2t. And now we just have to solve the problem for t. All right, and so it says, let's see, 0.2 and negative 0.2. So I can do it either way. It doesn't matter which direction I go. I'm going to go ahead and try to not have negative time. So the strategy I'm going to do here is just to say plus 0.2t plus 0.2t to both sides. It equals 0.4, and that's why t has to be equal to 10 seconds. And then if you look up at the top, I did a check, which is always a good thing to do, and that's how I caught my error and didn't make a video with the wrong answer, is I went ahead and plugged in 10 seconds to that kinematic equation, and it tells me that the black cart would be at a position of 40 meters after this 10 seconds of motion. And then it tells me also that the purple cart would be at 40 meters. They're at the same place. That's where one cart overtakes the other. So always be careful and always check your work, and you can look at the details there for that one. All right, finally, this last one. Starting from rest, a brick slides along down a icy roof with a constant acceleration. So the brick is sliding, and it says it starts from rest. So the v initial x is equal to 0, of course. We got our brick here, and it says it slides down the icy roof with a constant acceleration of 4.9 meters per second squared. How fast is it moving when it reaches the edge of the roof? 0.9 seconds later. So we're going with 0.9 seconds as our time. Remember, sometimes what you don't know tells you more than what you do know, okay? But actually, this is a pretty straightforward one. It says, how fast is it moving? And that would tell us how fast are we moving later. Let's see if we have enough information to leverage this equation. All right, Vx is 0 plus Ax times t. Well, the velocity that we're traveling down the roof is going to be related to our starting velocity plus the acceleration we experienced, 4.9 meters per second squared, times the time that we were undergoing that acceleration. And so actually this one is, wow, this is super easy. We should have done this one first to boost our confidence, right? 4.9 times 0.9, that would be 4.41 meters per second for a final speed at the edge of that roof. Sorry guys, PowerPoint's really messing with me here. All right. The thing about the kinematic equations is they work in both directions. I'll give you a really short note for this one. Let's say we have the Donald sending a message of love to you. All right, and he throws it down from the penthouse suite. It says, assuming the floor is 3.5 meters tall. So now we're going this way, right? And this would be like y equals 0, y initial equals 0, and y final equals 3.5 meters. All right, but actually we're looking at, it says you fall several stories, so that's going to be 98 meters for your final position. It says he hurled it with a huge velocity, v initial y of 10 meters per second. How long does the message of love take to reach you? So the thing about falling things is that they all have the same acceleration. The acceleration in the y direction is always 9.8 meters per second squared, and I have that in this slide for you guys right here. Anytime something is falling, it accelerates at 9.8 meters per second squared. And so for this one, we would pick a kinematic equation. It would have to have time in it, and we also know some things about position. So for this one, we'd have to pick an equation with time, and the only ones are those first two. So if we take a look at this, you can basically just substitute in y for all the x's. So let me show you what I mean. V initial y t plus 1/2 a y t squared. All right, and so you can use this equation on your kinematic equation sheet with just all the y's. And if you go ahead and do this one, you will find the answer, and I will post the answer here in the comments to this video below to see if you can get there. All right, that's Kinematics Introduction Basics. This is Mr. Simpkins in the Simpkins Physics Corner. Check out the comments. Leave your own while you're at it to find the answer to this one. I'll see you next time.